When we think about computers, we often think about programs and data, and the programs manipulate the data in some way. But the distinction between programs and data is really artificial. Both of them are stored in the same memory, and both of them are represented as bit strings. So if we have a bit string, it's not actually obvious whether it's a program or data. In some sense, it can be both. This becomes really obvious when you look at certain scripting languages like JavaScript. If you open this in a text file, then you can edit the program, you can edit the text, you can edit the JavaScript. But then if you feed it into a JavaScript interpreter, it suddenly becomes a program. It gets turned into instructions for the machine. A similar thing happens with Turing machines. Turing machines can be represented as bit strings. The main thing of a Turing machine is the transition function, and we can write this transition function down in a table as we've done before. And of course, we can encode this table in some way as a bit string. So every Turing machine can be represented as a bit string. A small technical note here, we will from now on assume that the reverse is also true. So every bit string we could have can also be interpreted as a Turing machine. This assumption is not really needed. We could get rid of it if we had to, but it makes some of the arguments a bit simpler. So let's say every Turing machine can be represented as a bit string, and every bit string represents some Turing machine. Because a Turing machine is a little bit like a program, we can now ask ourselves whether it's possible to execute a given program. So if we have some bit string that we can interpret as a Turing machine, then can we somehow feed this bit string into an interpreter that then executes that machine? And indeed, it's possible to do this in the following sense. We can build a Turing machine that acts like an interpreter. So it would get as an input a bit string that represents another Turing machine and some input x, and it would simply simulate what this other Turing machine that is encoded in this input would do on this input x. We call this a universal Turing machine, because in a way we can now program this Turing machine rather than hard encode the program in the transition function. There exists a Turing machine, U, such that for every alpha and x, the result of U executed on alpha and x is equal to the result that we would get if we would execute M alpha on input x, where M alpha is the Turing machine that's represented by the bit string alpha. Moreover, if M alpha halts on input x within t of size of x many steps, then the universal Turing machine will halt on this input alpha x within c times poly of t of size of x many steps. So the running time of the universal Turing machine will be polynomial in the running time of the original machine M alpha. The constant c here only depends on the parameters of the machine M alpha, but it does not depend on x. We frequently make use of the fact that universal Turing machines exist. And in particular, we make use of the fact that Turing machines can simulate what other Turing machines would do.